Hi, everyone, and thank you for joining my session today on choosing the right table format for your transactional data lake. I am Shana Schipers. I'm a specialist SA in analytics focused on big data at AWS, where I work with customers, a diverse range of customers across the globe on building and operating their transactional data lakes on AWS. So for today, what we'll go through is how to choose an open table format for your transactional data lake. But before we get there, I actually want to take a step back and evaluate whether you need a transactional data lake in the first place. Then we'll move on to open table formats and how to choose between those popular ones. And we'll go into some example use cases as well to make it all a little bit more tangible. So we'll go into partition evolution and change data capture, or CDC, as we all know it. And then I think we're close to my 30-minute mark here for this session, and then we'll wrap it up. So with that, let's just dive right in, I would say. And so first of all, I wanted to check with you whether, before going into Hoodie, Iceberg, Delta, those popular formats, do you need a transactional data lake in the first place? Because, this is a very hot topic. And so oftentimes I get customers asking me like, oh, which one of these three should I use? But the most important thing is, figuring out first whether you need any of the three at all, whether they will bring the features that you need or solve the problems that you're looking to solve, because not every data lake use case actually requires such format. So it's an important thing to figure out. So when I do that with customers, I typically start by asking them, like, do you have today like particular use cases on your data lake that you find challenging? And there are four very common ones that we hear that point in the direction of, yes, you will need a transactional data lake. The first one being data privacy and compliance. Think about GDPR. If someone requests their personal records to be deleted and you store those on a data lake, if you've tried it, that is quite, that's more challenging than it actually sounds. Finding that those records of that particular individual in all those thousands or maybe even millions of objects on your data lake, it can be like, looking for a needle in a haystack. So that is one use case we often hear that customers, struggle with on any kind of non-transactional or traditional data lake, if you will. Another one is change data capture, or CDC. Why? Well, change data capture, think of, capturing all the changes that happen on, say, a downstream relational database and then applying those onto your data lake as well. That requires record level updates, record level deletes, because that's what's happening on your database, right? Record after record gets inserted, gets modified, and so on. And basically you're capturing all that and then applying that onto your data lake. But those are two very different technologies. They store different data in a very different manner. And so that's oftentimes challenging on a data lake. Same thing for the third one, incremental pipelines, where, similar to CDC, you're replicating changes from, in this case here, from one database, or sorry, excuse me, a data lake layer to a downstream data lake layer, say from your bronze, silver, gold layers onto one another. But here is an additional challenge that you first, need to be able to find out what is actually changing on the source layer, if you will. What has changed? What do you need to replicate onto your downstream layers without overriding entire partitions or entire files, because it's not so easy to know what exactly in a file, what record got modified, for example. And then last but not least is managing table performance. So regardless of what query engine or read engine you use to query your data lake, what you might notice is that over time, you see your query performance degrade, slowly over time. As your data volume grows, your data set grows, you have more partitions in that data lake, you'll see that query performance actually negatively gets impacted over time. And so, because on a data lake, managing stable or consistent query performance, regardless of how much your data volumes are growing, or how many partitions you're adding over time, that is also a particular challenge we hear from customers. And so if any of these four already, if you're like, okay, this is exactly what I'm dealing with, well, then you're in luck. You already have your answer on, yes, you will likely need a transactional data lake. But you might be like, this is all great, but these are not really the use cases that I'm struggling with on my data lake. I have more like granular challenges. And I often hear that from customers as well. So they can be facing more specific challenges, like on the slide here. So the first two ones I already covered in the previous slide in the use cases, so I won't go into those again. But the last three ones here, I want to touch on. And for example, the third one on having concurrent writers and readers. So on a data lake, if you have multiple applications writing to the data lake, multiple query engines or people analyzing the data at the same time as writers are writing, you kind of, don't want them to conflict with one another, right? So you don't want one to override the changes of the other. You want your readers to have a consistent view and so on, to make the data lake usable at scale and for important use cases. So that type of concurrency control, as it's called, is something that is very typical on databases, but not on data lakes. And so that we see customers asking for as well, like they need that to make sure that, everyone is having a consistent view on the data. And then there is preventing table or data set corruption, because unlike, and you get to where I'm going with this, unlike a database, when you do something on a data lake, like uploading an object or writing a file, and it fails halfway through, you'll notice that that doesn't get rolled back, that doesn't get undone. So at that point, you're left with partial data that you wrote. You don't know at what point it fails, so you don't know what records exactly you would need to retry. But you have part of that data there. So at that point, you don't know what state your data is in. You cannot guarantee data integrity anymore. And so basically you end up with a corrupted data set. So that is also something, as data lakes grow to more and more use cases, business critical use cases, you always want to prevent that, of course. And then there is table schema evolution. So, things change over time. It's not uncommon to have fields get added to data sets over time, or things get renamed, a column gets renamed, or whatever you can think of, or data types change and so on. And what we often hear from customers is, regardless of where they built their data lake, they do not want to rewrite their entire data set just because a single field got added to their data set today, and they have been writing petabytes of data in the past. So these things are, pointers that if you're challenging any of the four use cases that I mentioned before, or any of these, or multiple of these challenges on your data lake as you're trying to implement more use cases or grow your data lake use, then okay, I need to think of a transactional data lake. Now, the purpose of this session is not to explain you in detail what a transactional data lake is, because I want to get to the good part of how to build it and how to choose how to build it. But in a nutshell, if I have to put it really simple, basically think of a transactional data lake as putting a transactional putting a transactional layer on top of your data lake to give it database-like functionality or features on top of your data lake. So it's exactly what the name says, right? So you're going to expand your data lake with some of those typical database features, like you see here on the slide, asset transactions, indexes, concurrency control, and so on, to deal with the challenges that I have mentioned before, or make it the use cases that I mentioned before as being challenging easier to implement. So how do you build that transactional data layer on top of your data lake? You do that by simply adding an open table format on top of your data lake. And there we come to the gist of the session, and that is, what open table format to choose. There are three very popular ones that we see used on AWS, and that's Apache Iceberg, Apache Hudi, and Delta Lake. All these three are really great open table formats. I can't tell you that one is better than the other because that's simply not the case. They're all great options, and adding these on top of your data lake on Amazon Simple Storage Service or Amazon S3 will provide you with a transactional data lake that you can deal with these challenges. Now, before going into how to choose now between these three, I just wanted to give you a glance at an example architecture on AWS for such a transactional data lake, regardless of the format. Just to make it clear that, it's not as complicated as it often sounds. Architecturally, as you see here, not much is changing compared to a traditional data lake on AWS that you might already have. You can still choose what sources, data sources your data is incoming from, what AWS services or third-party tools you choose to ingest your data, whether that's batch or streaming. You catalog and secure your data with fine-grained access control, still with the same AWS services or third-party tools, if you wish. And you still have that flexibility of, adding consumers for different use cases, allowing your consumers or readers to choose their tool of choice, what best fits their needs. And in the middle, you have your storage layer, your data lake, still on Amazon S3 as you would otherwise. It's just that now your data is stored or written in an Apache Iceberg, Hudi, or Delta Lake format when storing it on Amazon S3. So your ingestion and your consumption needs to be able to write and read respectively from into that format. But that's architecturally, not changing much. So just wanted to clarify that because it often sounds way more complicated than it actually is. But okay, so with that, the gist now is to actually help you choose between these three or how to go about that. So let's dive into that part on how to choose your open table format. So the thing here is, it's not a simple question to answer. I wish I could, but I cannot give you a decision tree where you would go along and say, okay, if you do this or if you have that, then choose that format, but otherwise choose that format. I wish it was as simple as that, but it's there's way more to it, unfortunately. But we need to start somewhere, right? So we look at typically at two very important factors to consider when supporting customers on this challenge. And the first criteria I usually tell them to look at is supported integrations. Why? Well, remember the architecture I just showed you? Well, you probably already have a data lake. You probably already have AWS services or other tools that you're using for data, for writing your data. You already probably have, your data consumers that are used to the tools that they're using and the AWS services, and they kind of, you likely want to keep that. So regardless of what technical capabilities or features a table format offers, it's very important to make sure that it's actually, it can integrate and it can work seamlessly in the environment or the current architecture that you have. Because otherwise, if you can't read from it or you can't write to it, there's really no point in using any table format at all, right? So that seems basic. However, take this into account that these table formats evolve so rapidly. They're open source table formats. They have huge communities of contributors. And so integrations get added rapidly. The same thing goes for AWS services or third-party vendors. Basically everyone out there is adding more and more support for these table formats on a daily basis. So make sure, depending on your timeline of your project, to also take into account the roadmap, or planned integrations, just to make sure to give you a whole view on the thing. Then the second thing to consider is functional fit. So once you have established that you can use this format with all your, query engines and ingestion engines of choice, and you're still left with a couple of choices in the table formats, which is most likely, then you can look at the functional fit of the table formats for your use case. Meaning, what features do they offer, but more importantly, what features or benefits does your workload require? Think of, for example, are you trying to implement low latency streaming workloads, or are you trying to optimize the query performance on your data lake? Those are two very different things. And depending on what your workload needs or what your requirements are, you want to evaluate the table formats on do these offer the features that you need to achieve the requirements of your workload easily and efficiently. So the rest of this session, I'm going to go into two examples on this functional fit. There's no point for me to go into supported integration. This is a highly individual thing to consider, right? So it wholly depends on your environment. But for the functional fit, I want to guide you through two examples quickly to give you, to make it a little bit more tangible what I'm talking about and how to go about such evaluation. Okay, so with that, the first one I want to touch on is a simple one, partition evolution. And as you'll see here on my slides, we'll look into this one for Apache Iceberg. So say you have an example architecture, just an Apache Iceberg dataset on Amazon S3, and you query that using Amazon Athena for ad hoc SQL queries on your data lake. Say, until February, you have been partitioning by month. You see here a column from month for January, for February, and everything was great. But you notice query performance in Amazon Athena is degrading a little bit. You see it's scanning too much data, and you notice that, not going into the details here, but you notice that partitioning by day would actually make more sense and would improve your query performance. At this point, you really do not want to overwrite, rewrite the entire data set that you've written for the previous months. So with Apache Iceberg, what you can do is a simple alter table statement, the SQL statement that you see here on the screen, and just doing a metadata operation of changing the partition schema of your table. And from that moment onwards, so from March here, you'll see that, as you keep writing data, now it will be written in a daily partition. So you'll see that on Amazon S3, you have a folder per day instead of per month. But these monthly folders for the previous months are still there. So when you go to query your table and say we want to select some data here, this query between the 11th of February and the 18th of March, which touches on our monthly partitions still, and then the daily partitions. Also, that is very seamless with Apache Iceberg, because what it does is it does a split query plan, basically, where a part of the data, the part that was written with the monthly partition gets read with that partition spec, and the part of the data that got written with daily partition simply gets read with that partition spec, and it all combines that data, puts it together, and returns that result seamlessly. So you don't even notice, and you don't have to know as a consumer that partition has changed or anything. So all of this is very seamless, changing under the hood, and it's nothing more but a metadata operation because of how Iceberg stores partition information and as metadata on the data lake as well. So that makes it very seamless. So at this point, you might ask me, do I need to use Iceberg in this case? If I ever need to do that, you might want to, you don't have to. It depends, it always depends. So look at how often you expect partitions schemas to have to change and so on. If you want to do the same thing with Apache Hudi or Delta Lake, you can, of course, change your partitioning, but it will require you to rewrite your dataset. So that is a cost or a trade-off to make for yourself, and depending on the frequency with which you expect to have to go through a partition evolution, whether the efficiency of this is crucial. Then this is the first example. The next example, I'm going to start one on Apache Hudi for change data capture. And just looking at a very simple example architecture here, where we have a database and we capture all the changes with database migration service, DMS. onto a raw layer on S3, and then we have Amazon Elastic MapReduce EMR using Spark, write that into a hoodie table dataset on Amazon S3. How would we do such thing in Apache Hoodie? Well, actually, before I go there, let me just give you a little bit of explanation on what would be going on here, because we're capturing CDC data in this case, change data capture data that will be stored in the raw layer. And that data basically depends, the format of that record depends on what CDC tool we use, DMS here. DMS would add some fields to the data to indicate, operations that happened on the database and so on. So that gets stored here, and then the job of our Spark application is really to translate the records that DMS generated into hoodie data and merge that correctly with the existing hoodie data on your data lake. So basically what we're going to look at now, how to implement this with hoodie, is this part, this Amazon EMR part. What would that look like on hoodie? So the good thing, the nice thing about Apache Hoodie is that it offers a utility out of box. So let's think of this as a prepackaged Spark application that you don't need to write any code for. It's just a utility that Hoodie offers that you can start using like this in a Spark submit. And this utility basically is performs streaming data ingestion from a variety of sources into a variety of data targets, one of them being Amazon S3. So it can capture everything seamlessly that has changed here in our source layer and apply that into our hoodie data set. And all the logic in between that we need, that CDC needs, that streaming ingestion needs, checkpointing, and so on, all of that is taken care of. So a few other things to note here is that you can, with Apache Hoodie, say that your record payload is a DMS payload, see here on the slide. That means that you basically tell Hoodie, and I'm going to provide you these records here in DMS format, and Hoodie will know how to interpret those records and apply those into a Hoodie dataset. You don't need any of that knowledge yourself. It also does the deduplication, making sure that if, in a single write, there are multiple updates to a single primary key, it doesn't, write those two records, but only applies the latest one so that you don't end up with duplicate data, basically, or you still have your primary key being unique. So this is the combined for upstairs that I marked here, and the source ordering field that it uses to do that. So all of that gets done for you, and you don't need to worry about it. And even with partial updates, and without going into the detail here, you can provide a Hoodie configuration saying, I will provide you partial updates only for my CDC. What does that mean? Say we have this Hoodie table existing already on our storage with 2 IDs and so on, and we would add a new record, where we only specify the fields that have changed, the primary key, but not the, this name field that hasn't changed. What we want to do is we basically want to tell Hoodie, look, we're going to upstart something in partial update mode, and Hoodie will know how to perform that update onto the existing data record on storage without overwriting this name field as null, without taking this literally, basically. So also that is a very useful feature, because depending on your CDC tool, depending on configuration, this might be common. Now, being conscious of time, just quickly want to go over how would you do this, for example, with other formats? Because is that possible? Absolutely, yes, you can. And we're going to look at an example here for Apache Iceberg, but I refer to the blog that I mentioned at the bottom for more details, because being conscious of time, I won't go into the details of the code, but basically to give you a sense of what it looks like if you would want to implement this with Apache Iceberg, you would have to basically write a deduplication logic on your incoming data and reordering your incoming data so that everything gets applied to your final data set in the same order as it got applied on your database, end up with a correct replica of your database, that data set on your data lake. You would need to write something like this. With a window function, you sort, you filter, you deduplicate your data. And then you basically have your data pre-processed, and you would go into merging that data, the one that sits here, basically onto your transactional data lake in Apache Iceberg format, saying, okay, now you need to know a little bit about how DMS writes, saying, okay, I know it writes a field for deletes and so on. And you basically then customly implement, just with these few lines of code, of course, customly implement how to process that data, applying deletes first, then updates, then inserts, and making sure that you do all of that in the right order to end up with a consistent data set. So that is what it would look like if you would do that yourself. And then for partial updates, also, of course, like same example as we looked at for Hoodie, also possible again with Iceberg, but with, again, some extra steps and a little bit of coding for you to do yourself. So the same example, if you would apply this new record with a null field, a partial record, you cannot simply do an upsert. You would first have to read the current version of this record to get the field value for this. And then you would have to do this merge logic that Hoodie did for you yourself and basically update, upsert the merged record where you overwrite null with the name A, in this case, into the Iceberg dataset. So this is CDC. Again, can you do it with all three formats? Absolutely, yes. If you have many CDC use cases, would you benefit from Hoodie versus Iceberg? Maybe you would benefit from Hoodie more because it will make it easier to get started. But again, very personal. You can do it with all three, and whether these, these features or this efficiency and this out-of-box support is important, that is up to you to decide based on your specific situation. Okay, so I think I have about 2 minutes left now, so I want to quickly wrap up with some key takeaways. First one being, do you need a transactional data lake? Well, remember the use cases that I talked about, but basically if you need record level updates, deletes on your data lake, if you want to make sure that you have good query performance over time as your data set grows, or if you want to ensure data integrity and consistency on your data lake, then yes, you do need an open table format on top of your data lake. But then which open table format to choose? You might say by now, she didn't give us an answer on this. And you're right, you're actually right, because I actually cannot, because it's such an individual choice that depends totally on your situation. But we can only give you guidance on actually, what to consider for your specific situation. And that is, most importantly, support the integrations, the ecosystem of the open table format, but also the functional fit depending on, your use case and other criteria that you might have for the workload that you're looking to implement. If you want more details and more examples for evaluating functional fit, have a look at this AWS blog post that covers more like these examples that I went through, the two previous ones. But with that, I just want to thank you for joining in here today with me. And I hope you enjoyed it, and I hope you enjoyed the rest of your sessions as well. Have a good rest of your day. Bye.